Okay, so we're going to start the limits unit. You can take notes. I'm going to send you my notes so you can watch. So when we talk about limits, we use the word approaches. That's the important word, approaches. So when we say approaches, we really mean gets really close to. And so we're interested in what happens to functions as we get really close to an x value. What happens to the function? So we're going to start off with the example y equals 2 to the x minus 1 over x. Now, you can see from your graph, so let's take out our graphing calculators, please. I'm going to be working on the graphing calculator with you. Oh, you know what? Yeah. So let's take out our graphing calculators. I'm going to be describing it. I'm going to be describing it as we go along. So let's enter this function in the graphing calculator. Hold on one second. Sorry about that. My calculator's just loading up. Nice. Okay. So add a calculator. Oh, whoops. Sorry. Control, doc, add graph. Okay. My first function is open parentheses, 2 raised to the x, space, minus 1, close parentheses, divided by x. Divided by x, enter. And what you'll see on your graph, like I see on my graph, is it kind of looks like an exponential function, but it turns out there's something called a hole here because 0 is not defined here. And what we're interested in figuring out is what exactly is that f of x value, right? So the question is, so I know as x approaches 0, right? As x approaches 0 from the left and the right, f of x approaches some value. It's obviously coming to some value. As I said, we might not get there, but we are approaching. It turns out that the answer is 0.693. Now, how do I know that? Well, I know that because I looked at my graphing calculator. So you're on the graph page. I'm staring at you right now. You're at the graph page. You're on the graph. You're going to go to Menu, Table, Split Screen Table, and on the right you see a table of values. If you scroll down a little bit, you'll see that for 0, it's undefined, which makes sense. The next thing you're going to do is go to Menu, but the thing is, I want to get really close in there. I know that this value is somewhere between 1 and 0.5. I want to get closer, so you know what we're going to do? We're going to go to Menu, Table, Edit Table Settings. I'm going to table start at 0, and my table step is going to go at 1/100ths. So 0.01. Now let's hit OK. There we go. Let's move it down a little bit. We can see that we've really zeroed in between. So let's write this table of values down just quickly. Let's come from the left and from the right. So from the left, we have negative values. So for example, negative 0.02, negative 0.01, we have 0, and then 0.01 and 0.02. Let's start from the left. What's going on from the left? Well, we have 0.68835, and then we have 0.69075. At 0, it's undefined. We don't have a number. At 1, we have 0.69555, and at 0.02 or 2/100ths, we have 0.6979. Now, you ask, how do I know 0.93? Well, you know what? I can get a little closer if I have to. Let's go back to Menu, Table, Edit Table Settings, keep my original point at 0, but add another divide by 1,000th. So 0.001. Let's see if we can get a little closer. There we go. And we see it's somewhere between 0.69290 and 0.693387. So that's the idea. So if you notice, I approached 0 from the left. And if you notice, I approached 0 from the right. Approached 0 from the right. Okay. And at the same time, as we came from the left, f of x approached from below, right? And as we approached from the right, f of x came from above. But we came to that same point. Once again, you don't need to take notes, or you can. Let's do some notation. So let me get back to the screen so I can see where you guys are. Okay. Some notation. The limit as x approaches 0 from the left of 2x, is it plus 1 or minus 1? Minus 1 over x is equal to 0.693. So this is notation for approach 0 from the left. Now, that negative sign. Now, I would also say the limit as x approaches 0 from the right, that little plus sign of 2 to the x minus 1 over x, that also equals 693. So this notation is approach 0 from the right. Okay. Now, because these two values are the same, we can then say, notation-wise, the limit as x approaches 0 from both sides of 2x minus 1 over x is equal to 0.693. Now, what I want you to do is, what I'd like you to do on your own is, I want you to use the GDC to find the following limits. I want you to use the GDC to find the following limits at the following places. Use the GDC to find these limits. So let's see, I want you to find the limit as x approaches 2 of x squared minus 4 over x minus 2. I'd like you to find the limit as x approaches 0 of sine of x over x, and I want you to find the limit as x approaches 0 of x divided by radical x plus 1 minus x. Okay, now, I want you to say to me at this point, hey, Mr. Rather, why can't we use the L'Hopital's rule? Why are you making us do all of this? Well, this is an old school. You're not even responsible for this, but I'm giving you the old school. So just say, keep in your head, he's going to tell us something really easy to really make this go quickly. And I will. But we need to get through some things first. Well, once again, let's continue. We don't really care what happens at the point. I don't care what happens at 2, 0. I don't care. I just want to know what's happening right near it. So for example, I give you f of x is equal to a piecewise function. It's 1 where x is not 2, and it's 0 when x is 2, right? So the question is, what is the limit as x approaches 2? So you draw the graph. You say, that's easy, Mr. Adler. You say, that's easy. It's a line. I have a graph here. And what do we have? Let's see. It's 1 everywhere. It's 1 everywhere, except at 2. At 2, it's 0. And so the question is, what is the limit? What is the limit as x approaches 2? Once again, the function is 1 for everything, except at 2. But when x equals 2, the function is 0. That makes sense. The question, though, is what is the limit as x approaches 2? The answer, 1. 1. Once again, I only care what is it approaching? Once again, what is the function approaching? Well, as it approaches from the left, right, as x approaches 2 from the left, the limit as x approaches 2 is equal to 1. And the limit as x approaches 2 from the right is also 1. I don't care that it's 0. I just want to know what's going on right near it. 1. Therefore, the limit is 1. If the limit from the left and the right are not equal, we say the limit does not exist. So, once again, you're going to see this in my notes. So, for example, f of x equals absolute value of x over x. So you might say, well, that kind of looks like 1. Well, it kind of is, except, first of all, where does it exist? Well, there's 3 sections to look at. Positive numbers, negative numbers, and 0. At 0, there's a hole. So the question is, what is the limit as x approaches 0? So I'm interested from both sides. Let's see if it exists. Well, I know if x is positive, I have like x over x, so this is 1. Once again, if x is greater than 0, I have x over x, and therefore it's 1. But if x is less than 0, I have positive x over negative x, it equals negative 1. So, let's see. What we see here is that the limit as x approaches 0 from the left is equal to negative 1, and the limit as x approaches 0 from the right side is positive 1. So, because the limits are not equal, we say the limit does not exist. Now you might say, this is the continuity thing we were talking about. It's a discontinuity, and you might say, wait a minute, that's that thing about the removable discontinuity. And the question is, can I stick something in there so I can make this line continuous? In this case, it's not a removable discontinuity. We call this literally, like you can see it, this is called a jump. Fine. We'll get to that. Also, when is another case when we say the limit does not exist is when the limit is unbounded. So, for example, you'll see in my notes. So, for example, if I ask you for the limit as x approaches 0 of 1 over x squared, 1 over x squared, you can look at the graph of this. You look at this graph of this. You look at the graph, right? And you kind of know, because you practiced this, the logic would be in my head, I know that 1 over x looks like this. Therefore, if I'm squaring it, it's both on top here, right? And we know the asymptotes. We kind of know it looks like that. The question is, what's going on at the zeros? And so you say, okay, well, the limit as x approaches 0 from the negative 5, it seems to be unbounded. It's just going up. We say it's infinity, right? That's the idea. Unbounded, there's no upper limit. It just keeps going up. It's infinity. Also, the limit as x approaches 0 from the right side is also unbounded. You can see that. You can see that. It's just going up. It's just going up as we get closer to 0. It's just going up towards infinity. It's also unbounded, which is also infinity. Now, you might say, hey, Mr. Rather, they're both going to the same infinity. It doesn't matter. If a limit is unbounded, it does not exist. Limits have to be, in this class, limits have to be real numbers. So, limits must be real numbers. You know, this summer I took a class in complex numbers. It needs to be a number. It just can't be infinity. If it goes to infinity, the limit does not exist. Okay, let's talk about some properties of limits. Let's talk about some properties. Properties of limits. Once again, you're going to say, Mr. Ryler, why can't we use L'Hopital's rule? You can. You got to go through this. You have to sit through. You might go to college. You might have to sit through these lessons. Properties of limits. Properties of limits. Now, the easiest way to figure out the limit is by substitution. Easiest way is by substitution. So, for example, I might say to you, find the limit as x approaches 5 of 2x plus 3. And you might say, oh, let me get out my calculator. And someone else might say, wait a minute. I know what that graph looks like. That's this graph. And I know that there's a discontinuity. There's no holes. There's no asymptotes. So that means I know what the limit is. I know when x is 5. I know when x is 5. I know that this is going to 13. And you'd be right. For example, you don't need to do 4.9. You don't need to do, 2 times 4.9 plus 3 is 9.8 plus 3, which is 12.8. And then you would say, oh, no, let's do a 5.1 plus 3. And so you have 10.2 plus 3, and you have 13.2. You would argue, well, it's approaching 13. Well, just substitute. Just substitute and hope it works. Most of the time, it's not going to work. And I'm going to show you a method once again, but see if it works. Always substitute. 2 times 5 plus 3, 13. That's your limit. Now, that substitution method is really great when you have like polynomials. Nice polynomials, trig values, exponentials. Once fractions start getting introduced and radicals, it gets a little messy, but I'm going to show you a quick way. So, let's continue. So, therefore, the limit as x approaches a of a constant is the constant. And the limit as x approaches a on a line is just the value at that, like we saw here. For example, this is the perfect example. Just stick the value in there, and you got that. So, for example, the limit when x approaches 5 of the linear 2x plus 3 is 2 times 5 plus 3. You can do linears. The book also just kind of mentions, as x approaches a, for example, x to the n, what's the limit? A to the n. Plug in quadratics, cubics. It's nice and basic. The other thing you need to know are some basic rules of limits. There's some basic rules of limits that are helpful. So, for example, this is kind of cool. Scalars. So, for example, and I apologize. So let's make 2 limits. I'm going to say the limit as x approaches a of f of x equals L, and we're going to say the limit as x approaches a of g of x equals m. Okay, so we can deal with scalars. So for example, if I say the limit as x approaches a of c times the function, well, that's c times, we can pull the c out, and we have c times the limit of f of x, which is L. Very straightforward. What do you think about addition and subtraction? What's the limit as x approaches a of f of x plus or minus g of x? It's what you think it is, L plus or minus m. How about the product? What's the limit as x approaches a of f of x times g of x? It's what you think it is, L times m. The quotient, what is the limit as x approaches a of f of x divided by g of x? It's what you think it is, L over m. What's the one condition? G can't be 0. As I said before, you're going to say, Mr. Adler, why are we doing this? Just tell us L'Hopital's rule. You gotta wait. And then you can forget all this. So once again, g of x can't be 0. And then the power rule works for powers also. It's kind of cool. The limit as x approaches a of f of x to the n power is actually the whole thing. The limit, this is kind of really awesome, of a of f of x, the final answer raised to the nth power. That's kind of cool. So, why do we need this? Well, old school, you would be given a problem like the limit as x approaches 2 of 4x squared plus 3. So how do we apply the rules? Well, the rules say this is equal to the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. What's going on here? Let's pull the 4 out. 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. What's going on here? I can say 4 times the limit as x approaches 2 of x, the whole thing squared, plus the limit as x approaches 2, 3. And then we just apply some of our rules. Well, this is 4. We just substitute it right here. That's 2 squared. And we know the limit of a constant is just the constant. Well, that's 16 plus 3 is 9. Or you can say, Mr. Adler, why did you make us do all that? And I'm going to say, oh, because you have to do the old school way. All you could have done was just plugged it right in. 4 times 2 squared plus 3 equals 19. But these are the limit rules. If you have to sit in a college class, okay. Now, once again, I'm going to show you some tricks. You're going to say, Mr. Adler, just show us L'Hopital's rule right now. And so I'm going to say, no, I have to show you this. So once again, maybe you can look to the end, that's fine. I'm going to go through this. And you can say, once again, Mr. Adler, you're wasting your time. Okay, what is the limit as x approaches 1 of x cubed minus 1 over x minus 1? Well, you plug it in and you get 0 over 0. So you say to yourself, maybe I can factor something out. Well, it turns out if the numerator and the denominator have the same factor, the graph is going to be a hole. I think we discussed this in the class. So what turns out, that this ends up being x squared plus x plus 1 times x minus 1 over x minus 1. Oh, look, this ends up being a parabola. It looks something like this, I think. Yeah. And there's a hole at 1. And the idea is cross out the factors and then substitute it in. So we have 1 squared plus 1 equals 3, and that's the limit. So that's the trick. Whenever you get a polynomial over like a linear, see if you can factor it and cancel each other out. Good. The next, so this is called cancellation. Cancellation. Another trick is called rationalization. Rationalizing. Do you need to know this? No. L'Hopital's rule is going to make this easier. But if you sit in a class through college, you sat through this with me. For example, the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Okay, when you see something like this, yes, I will show you L'Hopital's rule, but how do we deal? It's called rationalization. The trick is, sorry, let me close my pens. The trick is multiply the top and by the conjugate to get rid of the 0. So why do we have to do this? Well, the first thing you're going to do is substitution. So you substitute this in. So when you substitute, what do you notice? Substitute. It's going to have the square root of 1 minus 1 over 0, 0 over 0. So the trick is, to rationalization. So rationalization, what we're going to do is you're going to multiply the top and the bottom by the square root of x plus 1 plus 1. And on the bottom you have x plus 1 plus 1. So what does this result in? Well, the denominator is now x times the square root of x plus 1, plus 1. What's going on in the numerator? We have x plus 1 times x plus 1, which is x plus 1. We know from the FOIL method and the difference of two perfect squares that these, like the middle term, the last and the inners cancel out, and you have 1 times negative 1. Well, this ends up being x over x square root times the square root of x plus 1 plus 1. These x's cancel out. I'm going to do it up here. And you end up with 1 over the square root of 0 plus 1, which equals 1/2. So the limit of this function as it approaches 0 is 1/2. You can check this in the calculator. Okay, let's continue. Okay, I'm gonna stop this video now.